Okay, so for these three problems, okay, we have, once again, first order differential equations. And so for the first item, we have dy over dx is equal to 4x plus 3. And if I separate the variables, in this case, separating the differentials, dy and dx, okay, so I'm going to have dy is equal to all of 4x plus 3 dx. And here, upon separating, I can once again integrate, and for the antiderivative of dy, because that will go to y, and again we'll just have the constant resulting from the integration to be on the side where the independent variable exists. Okay, so for the antiderivative of 4x plus 3, okay, so we have 2x squared plus 3x plus the constant, and the result here, that's going to be the final result. Okay, so just a fairly quick answer item. Now for what we have in the next problem, we have dy over dx is equal to 2y over x, and if we look at separating the variables, okay, so we can divide by y and multiply by dx simultaneously. Okay, and since we're solving for y, okay, we can say we have dy over y, and you can say we have is equal to 2 over x dx, and upon separating the variables, okay, we can integrate. And for the antiderivative of the reciprocal of y, okay, so that will go to the natural logarithm of the absolute value of y. And for 2 over x dx, you can say that the antiderivative, okay, we'll say we have is equal to 2 times the natural logarithm of the absolute value of x, followed by the constant. And what we can do here, just like alternating between exponential and coefficient positions where we have logarithmic terms, okay, we can make this 2 into an exponent. And regardless of whether x is technically positive or negative, the squares of positives and negatives will be positives. And we can say that in the rewrite, okay, for 2 times the natural logarithm of x, we can go ahead and say that that is going to be the natural logarithm of x squared. And once again, liberating, okay, what we have in the variable y, okay, from the natural logarithm, we can apply the natural logarithm of exponential base e to both sides. So for what we have on the left, okay, so we have e to the natural logarithm of the absolute value of y. Okay, so this becomes the absolute value of y. And for what I have to the right, again, just taking the reverse of the product property. And again, we have, once again, reappearing, we have e to the c, and we say that is going to be equal to a constant. We'll just call this, once again, letter A. All right, and so for what we have now, we have the absolute value of y is going to be equal to A and e to the natural logarithm of x squared. That part will go to just x squared. And taking care of the absolute value sign, in other words, going from the absolute value of y to just y, we have y is equal to technically plus or minus ax squared. And for what we have technically for plus or minus a, we'll let this just go to the variable, we'll say beta. And so we have in this case, we can say that we had that y is equal to beta x squared. And for what we have in the case of the third problem, very basic. Okay, in fact, more basic than what I had initially intended. Okay, and so we have separating case. So kind of wrapping things up in a nutshell. So we have separating dy and dx. So we have dy is equal to 2x dx. And separating and integrating. Antiderivative of dy goes to y. And for what I have on the right, okay, this comes out to x squared plus c. Okay, so we have with the first and third problems, okay, the arbitrary constant is c, whereas in the case of what we have in the second problem, okay, the arbitrary constant ends up as beta. All right, and let's say that just sort of a refresher in terms of solving for y. I'll give you one that is a little bit different. Okay, and this is going to be working with the natural logarithm of exponential base e. And let's say if we have dy over dx is equal to, and we'll say that we have dy over dx is equal to 4x times e to the x squared over 8. And if we look at separating, once again, the differentials, okay, so we can say that dy is equal to 4x times e to the x squared over 8 dx. And again, separating, okay, we can now integrate. Antiderivative of dy goes to y. And what I think I'll do here is just sort of stepping over to the side here. Okay, so you have with the integral, okay, so you have 4x times e to the x squared over 8 dx. And for what I have here, I can perform u substitution. Okay, and so we have, in this case, right, so we have the derivative of the variable exponential expression that we have to which e is raised. The derivative, again, is going to go to a first order x term. So we have through the pathway of u substitution. Okay, so we'll set u equal to x squared over 8. And this will create, upon taking the differential of both sides, we have u goes to du, and for x squared over 8, okay, so derivative is going to be 2x over 8, so this will go to x over 4 dx. And guess what? Expressing dx in terms of du. Okay, so I'm going to have taking the reciprocal of x over 4. So again, dividing by a fraction is the same as multiplying by the fraction's reciprocal. So we have 4x, or 4 over x du is equal to dx. And so setting things up along the parameters of u substitution, so we have 4x, and this will be times e to the u, and we have for dx, again, I have 4 over x du, and here we can do a bit of multiplying. So here we'll have x's to go out, and 4 times 4 is 16. We have times the integral of e to the u du, antiderivative of e to the u du, so this will go to e to the u. So here we'll have 16 times e to the u, followed by the constant, And we have upon back substitution, we have 16 times e to the x squared over 8 followed by the constant. Okay, so going back to what we have here. So we have y is equal to 16 times e to the x squared over 8 followed by the constant, and boxing this in, okay, and that is going to end up as the final answer. Also, another thing that we have regarding separation of variables, and some textbooks might leave the answer in terms of second degree in the dependent variable, and if you were to do that, that's fine. Okay, but let's say if we have dy over dx is equal to x over y. And if you notice this time around, okay, so separating the variables, we'll be looking at multiplying by both y and also by dx. So left hand side, we're going to have y dy is equal to x dx, and separating the variables. Okay, so for y dy, applying the power property of integration. Okay, so antiderivative of y dy, this will go to y squared over 2. And to the right, x dx, antiderivative will have x squared over 2. And again, I'm going to apply the constant on the right-hand side. Okay, and if I multiply the equation by 2, so you see that we have y squared is equal to x squared plus 2c, and you have a constant times a constant. It's still going to be a constant. I'll just apply, let's say, like a letter k. So you have k is equal to 2c. And one way that you can express the final answer is that we can say that y squared is equal to x squared plus k. And many authors of differential equations textbooks will leave the final answer like in this format. But if I were to go any further, okay, you could consider the square root property of equality, where if I were to go from y squared to y, right hand side you'd be looking at plus or minus the square root of x squared plus k. And whether it is positive or negative would be contingent upon the types of initial conditions that would be imposed. Okay, so the versions, either version of how you apply the answer will suffice.